All right, hey everyone. Welcome to today's session. I just wanted to do a quick introduction. My name is Higgy Park. I'm a specialist solutions architect at AWS. I've been here about 6+ years, really helping customers like Capital One, working through serverless architectures, thinking about how do we not only enable developers, but how do we operationalize it? How do we put guardrails around it? How do we make this enterprise ready? So happy to talk, but go ahead, George.
Cool. Hey, everybody. My name is George, and I'm a senior distinguished engineer. I work for our retail bank organization, and I also lead our serverless center of excellence. So for those of you who live in the US, you probably have heard of Capital One. We're one of the top 10 banks in the US. For those who are international, you may not know that we're one of the top 10 banks. One thing that makes us unique is that in 2020, we closed our last data center, and we moved everything into the cloud. So we are actually all in on AWS, and we're basically the only major bank that has accomplished something like this. We're heavily invested in technology, and so what this allows us to do, being in the cloud, is to innovate faster and not have to worry about all of the what AWS calls undifferentiated heavy lifting, like managing servers, all that stuff. So today we're about 11,000 people in our tech organization. We have adopted a serverless-first approach. So everything we do is optimized for serverless, and we try to be heavy users of Lambda and Fargate where we can. And today you're going to hear a little bit about our experience on the serverless platform, some of the things that we've run into that hopefully after this talk you will not run into. And so we're excited to talk you through this, and Higgy's going to kick us off.
Yeah, so part of what we wanted to do is we're going to kind of play on each other a little bit in that kind of me as the AWS person, I'll share a little bit of the best practices that we've seen a lot of our customers broadly apply into their accounts, into their organizations as they're architecting and building. And then George, of course, will tell me how the best practices that I'm recommending just don't work for them, or the ways that they've stretched the bounds or have perhaps broken some of the best practices, primarily because some of the things and the constraints that Capital One has perhaps push the boundaries of what we want to do. And so we're going to kind of talk through some of those experiences. So the first one we'll talk about is for the developers in the audience, for people who are actually on their laptops or on their workstations building applications. Again, just a quick overview for those that may not be aware, there is something called this AWS Serverless application model. And really what this is just a framework that helps you as a developer to quickly describe your serverless resources and also has an associated CLI. So this is essentially open source templating language, similar to CloudFormation. It's essentially a transform on top of your CloudFormation. Now, what's nice for you as a developer is the SAM CLI tool. So when you're developing your serverless applications, maybe you're writing some Lambda functions, maybe you're using API Gateway, you may have a tool chain that says, all right, in order to be able to test or apply these changes, you may have to go through a pipeline experience. Oftentimes, if you have lots of robust unit tests, integration tests, linting, et cetera, these things can take some time for those deployments to happen, and that developer feedback can sometimes take a certain amount of time. What this SAM CLI allows you to do is to actually test your Lambda functions locally on your developer machine prior to committing it to a repository and prior to that entire pipeline process proceeding. So these are some of the CLI commands. I won't go through all of them, but SAM init essentially will allow you to instantiate or start that package. And then the build, package, and deploy are essentially that process of creating your artifacts, then of creating the template that will go ahead and actually do the deployment, and then, of course, deploy would actually push it into your account. This is just an example of again, the point here is not that you're actually going to read the entire template. But one thing that I often have customers asking me with SAM templates is, I have more than just a serverless component that I want to describe in my template. And so this is just an example of you can include both serverless shortcut or SAM template resources, but you can also include regular CloudFormation. So again, SAM is just a transform on top of CloudFormation. So all of the resources you might want to describe just using regular CloudFormation that may not necessarily be serverless resources, you can include them as part of your template. And for me as a developer, what I found is I enjoy actually the SAM CLI experience because, like for example, one thing that I do is in my developer account, I can do a SAM deploy, and I can see for example, the event log from my CloudFormation deployment in my console. So rather than doing a deploy and then having to go into the console and look at the output of the events, I can see that directly in my terminal. So that's one of the reasons why I like that experience a lot as a developer. Now, here's an example of me testing and doing some local development. Again, in that first orange line, again, not necessarily meant for you to see all of it, but you'll see that I'm injecting a lot of parameter overrides into my local invoke. And you'll see the bottom is an example of the output of what that local invoke might look like. And you'll see, in this case, I have a Spring API that's actually running inside of my Lambda function, and it has all of the outputs spit out to my local terminal. One thing that you'll notice here is that we are actually pulling, or in this case, I actually skipped the pull because it was already locally cached, but I'm pulling essentially a Lambda container image. And that's essentially the base image that will be used for emulating the Lambda function invoke on my local machine. Now, one of the problems, again, as I was working with George and at Capital One, is that the problem for a customer like Capital One is that it uses public ECR. And so Capital One does not actually support use of public ECR. They actually use their own internal Artifactory repository. And so again, just as a developer, the solution in this case would be you can actually add an additional parameter that specifies I want to actually use an internal Artifactory repository. So you could have an internal team, maybe an SRE team or a team that actually controls all of the images or artifacts that your organization is allowed to use. They could then pull in, scan, make sure that that's a compliant image, put that into Artifactory, and now you as a local developer can then pull that appropriate image for local testing.
Cool. So one thing we learned really quickly was that when you're building with Lambda and serverless, there's just so many different components. You have to standardize on a release process. So we've built a release process, and all of our teams internally are centered around something called one pipeline. So everything that goes out through production, across development, QA, and into production eventually goes through this pipeline. It does a lot of checks for us, including governance, risk controls, making sure everything meets our standards. And recently, we've begun to integrate SAM and CloudFormation into this process. So it's one of the greatest things about this, and I highly encourage you, if you're building serverless, is to deploy SAM locally and stay away from your deployment processes until you're ready to go. Because all of the steps you see on the right take a long time. Like they take 5, 10, 20 minutes, maybe an hour to get out to those accounts. Right? If you can do everything you can locally on your laptops, that will save your developers all of the round-trip cycles into AWS, essentially. Right? So raise your hand if you're doing SAM today, like using any kind of SAM. Cool. So we got like 30% of the people out there. Cool. Yeah. So one thing I think maybe you can take away from this talk is just go try SAM. I think it's probably the best tool out there in terms of developer productivity.
Cool. So another area that we were challenged, so on the deploy side, from a secrets management standpoint, let's just go with like an example here. So here's an example I built, I think a year or two ago when EventBridge had announced support for API destinations. And so one thing that you can do is you can actually create what are called EventBridge connections. In that EventBridge connection, you can specify secrets for integrating with other APIs. So in my example, I need to be able to inject API keys when I deploy this resource. So in the Slack example, if you've ever integrated Slack with EventBridge, you can send an event into EventBridge and then do this this EventBridge connection, which has that API key, which then talks to the Slack API. And then, of course, you would imagine you can configure it in a way that it hits a certain channel within your Slack environment. And so, again, the standard ways that you would think about doing this is from a deployment standpoint, you can use things like dynamic references in your CloudFormation templates when you want to inject those secrets. So these are just a couple of examples if you're using SSM or if you're using Secrets Manager. These are ways that within your template, you wouldn't have to pass them in as a parameter per se, or you wouldn't have to actually specify them statically, which of course you would never want to do. In the Slack example, here's an example of that connection resource. And you'll see at the bottom here, I specify the API key value for that connection, and then we're doing a dynamic resolution from Secrets Manager for that API key that I had to speak to my Slack API. And then here's another example. So I think about 2 months ago, we announced that we have a new Lambda layer or an extension that will allow you to do secrets and parameter injection into your Lambda functions. So one of the challenges you have is if you've had Lambda functions that want to connect to Secrets Manager, if you have large concurrency of your functions and all of them are trying to get secrets out of Secrets Manager, you're probably aware that there are API limits to Secrets Manager. And so in this case, what you can do is you can attach this extension. You can then configure it with certain TTLs. And it will then go and retrieve those upon cold start and then cache them locally. This way, every subsequent time, it will actually have that within a local cache. So this is just something that we've made available to you as a customer. We found a lot of customers were building their own local dependencies and doing some of this work on their own, so we wanted to release this as an extension. Now, of course, that's what we do, but at Cap One.
Yeah, so we actually don't do any of those things that Higgy was talking about. Not because we don't want to, but because we are a bank and we have slightly higher governance processes than the normal startup or unregulated industry. So we actually run our own secret store, and it's called, internally, we call it Chamber of Secrets. I think it's a Harry Potter reference, I don't know. But one thing we learned really quickly was that as we moved away from monoliths and into small Lambda functions, you can spin up concurrency like this. You can get from 0 concurrency to thousands of concurrency in less than 10 seconds in some cases. And you can go down to 0 in the same amount of time. So that caused immense pressure on our secret store. And it would cause pressure on basically any downstream service. So for those of you who have done Lambda to RDS, it's the same concept, right? You will overwhelm your database within minutes. So the solution that we came up with is what you see right here. Basically, we've created an extension, and that extension lives in a Lambda layer. So we attach that layer to all of our Lambda functions. And during the initialization process, so what AWS calls the cold start, the layer goes to Chamber of Secrets, fetches those secrets, caches them locally in the execution environment, and then serves them up in a local HTTP server. So anytime the Lambda function itself needs to run, it never talks directly to Chamber. So what it does is it just does the local HTTP get against the layer and pulls the cached secret. And there's a lot of other controls that allow us to tell that layer when to refresh the secret, how often to refresh, that kind of stuff. But so this is the concept that you all should take back. Anytime you have lots of Lambda functions talking to some kind of constrained resource, generally this is the type of approach that you want to do. Hit the resource, cache it, use it locally, and refresh it only when you need to. Right? So, yeah.
So another challenge that you can imagine is as you are developing and deploying your Lambda functions, as an example, you would want to ensure that you're doing this in a safe manner. So I think 3 or 4 years ago, actually, George, when he was at AWS, he wrote the launch blog for CodeDeploy integration with Lambda. And essentially, the idea here is you can use the CodeDeploy service to use weighted aliases, which will then say we can do, let's say, a blue-green or let's say a linear rollout or a canary deploy from version A to version B, as an example. And so in this example here, this is just an example of, again, a SAM definition of a function. And we have a couple of these parameters within the definition that help you do those safe deployments in a simple manner. So here you'll see that there's an auto-publish alias, which essentially says, for every time you do a deployment, we will automatically publish an alias for this particular version. And in this case, we've called it live traffic, which in the following slides, we're going to use that in another example. And then here you can then specify a set of different policies. So within the SAM definitions, we have a number of different policies. In this example, it's linear 10% every 1 minute. So basically, after 10 minutes, you'll have the full deployment out to the new version. The other interesting thing, too, here is, again, from a safety standpoint, you can do things. In this case, we've specified a pre-traffic hook. You can also do post-traffic hooks. So for example, if you wanted to check the existence of a key in a database or some data that you needed ahead of the deployment, you could write another Lambda function that would be your pre or post validation for that deployment. For example, on the post-deploy side, you could do something like we can do a smoke test against an API endpoint, make sure that endpoint is healthy, and if and only if it's healthy, then will we complete the deployment. Otherwise, we'll do a rollback. Now, I think George is going to go ahead and talk through some interesting findings that they had with fine-grained deployments?
Yeah, so one thing that I encourage you all to do is try to standardize your engineering conventions. So like this live traffic alias is something that we require on all Lambda functions that go out. And it's the exact same name. So that if I can jump into any engineering team at Capital One, and I can tell exactly where the entry point is for that service. Right? So any engineer can do that across Capital One. We know exactly how our Lambda functions start and where they finish. So that's just one example. So Higgy talked about rolling out code safely. And there's a cool launch blog that I wrote many years ago when I was with AWS. But it talks in detail about this. There's two primary rollout methods. Right? So there's a linear method. And linear just says, I want to roll out X% of traffic from my old version to my new version over Y minutes, right? So like this example that you see here says, roll out 10% of traffic from my old version to the new one every minute. So it's going to take 10 minutes to complete that rollout. The row on the bottom you see there is the secondary method, which AWS usually calls like baking in. So like typically, it's a canary method, right? So you roll out a small percentage of traffic to the new version, and you wait. You just wait and see if there's any problems with it. Right? In this case, it waits 5 minutes. But you can customize all of these and say you want to wait 30 minutes, an hour, or more. Right? So there is another method where you can do Lambda all at once. I probably encourage you to stay away from this one. This is you can do it in development, and we allow immediate rollouts in development, but we don't allow it in our upper level environments where we need to control risk. Right? So we've actually customized our rollout strategies. One of the most commonly used ones is a linear rollout over 45 minutes. So if you look at how this works, at minute 1, all traffic is currently sitting on version 1 of my Lambda function. And then when deployment starts, no traffic is on version 2. Right? Version 2 is rolled out, but there's no traffic being routed to it. So at the next minute, we move 2% of traffic. Right? And then so we're at 98% version 1, 2% version 2. And then we just keep moving forward, 4% on the new version, 6% on the new version, 8%, and finally 10% at minute 6. And it just keeps going on. It takes roughly 45 minutes. Sometimes it takes a little bit longer, a little shorter, because AWS, this isn't like exact science, right? It just, if you worked in AWS before, Lambda functions take plus or minus a few seconds. So we use something called provision concurrency a lot at Capital One. Like, who's used provision concurrency? Maybe 25% of people. So if you haven't used it before, PC takes time to allocate. Right? So what it does is it says, I want to allocate X number of Lambda functions and keep them warm all the time. And the reason you would do that is so that you don't have cold starts. Right? So you trade off a little bit of cost, a little bit of idle, for maximum performance and never any cold starts. So now, when you have a linear rollout, one of my developers one day was telling me that our 45-minute rollouts were taking 90 minutes or an hour and a half, 2 hours. And we really didn't understand why. We specified 45 minutes. So let's take a look at exactly what happens behind the scenes. So same thing, 45-minute rollout strategy that we customized. But this time, we have provision concurrency turned on. Right? So same thing, first minute, we're going to use a 10 PC allocation. So in this case, 10 warm functions at all times. Right? So the next minute, it's supposed to move 2% of traffic over to version 2. Right? But notice in this case, AWS has not provisioned any provision concurrency on my second version. And we're going to get to that really quickly, and I'll show you exactly why that happens. Minute 3, again, there's no PC being allocated to version 2. So what's happening is I have traffic being directed from version 1 to version 2, but there's no PC on version 2. So there's a couple side effects to that, right? You have cold start if traffic were to land on that second version. Minute 4 is when we first start getting PC allocations being moved from version 1 to version 2, and we'll take a look at exactly why that happens. So all Amazon's doing behind the scenes is basically a little bit of simple math. Right? So it takes the allocation that you specify, so in this case 10, And it's performing a percentage. It's multiplying 94% of version 1 and then 6% of version 2. And it comes up with 9.4 and 0.6. And then it just rounds up or down based off of whole number rounding. So Lambda determines that version 1 at this point needs to have 9 allocation of PC, and version 2 needs to have 1 allocation. So it isn't until your 4th stage or your 4th traffic shift that you have any PC being allocated to your new function. Right? So look at minute 5. The math just works out that there is no more PC that needs to allocate. Minute 6, same thing, no PC. Traffic is shifting, right? But there's no additional provision concurrency. And this has side effect, right? More traffic is going to your new Lambda function, but there's no extra provision concurrency, which will have downstream effects as more traffic gets routed to that function. So 7, 8, 9, and then 9 is when the next shift actually occurs. Right? So at 9, the same math happens, 10 times 84%, 10 times 16%, 8.4, 1.6. So that just rounds down to 8 and rounds up to 2. So Lambda determines that it needs to put an additional allocation on version 2. So now I have, at the 9-minute mark, I have 8 and 2, right? So 10 minutes, nothing happens. Provision concurrency stays the same on both versions. Minute 11, same thing. And we're just going to fast forward here. We mentioned a little bit that PC takes time, right? So it takes, like, in general, like 3 to 5 minutes to make any kind of modification to provision concurrency. And that's for small numbers. That's for, like, these little tiny double-digit numbers. If you have thousands of PC being allocated, it will take 10, 15, 20 minutes. So if we look at the 4th stage there, even though you're on the 4-minute mark, the elapsed time in that stage is 8 minutes. And then if you look at the 12-minute mark, it's supposed to be the 12th stage, but you're actually moving elapsed time at 17 minutes. Right? So let's fast forward a little bit more. Stage 19, right? At this point, it's taking CodeDeploy about 30 plus minutes to get to stage 19. And I specified a 45-minute rollout. So if we look at this, my rollout is not going to make 45 minutes. I'm not even halfway rolled out from my old version to my new one, right? So this caused a lot of developer confusion at Capital One. Like we were specifying 45 minutes, it was taking 90. We were specifying 90 minutes, it was taking 3 hours, right? So this is something you definitely want to watch out for if you have PC turned on, coupled with traffic shifting using CodeDeploy. The biggest impact here is you might actually miss your rollout window. If you're doing this in production and you expect to be done in 45 minutes and your traffic starts coming, like you should be aware of this. Like you should do this early and make sure it happens before this kind of stuff occurs. So we're going to shift into some resiliency patterns and talk about APIs.
Cool. So how many people in here are using Amazon API Gateway? All right, cool, a lot of folks. So how many of you folks have private requirements on your APIs? Oh, okay, significantly less. So for those folks that raised your hands, I'm sure you've probably felt this and experienced this pain. But in order to enable a private API gateway endpoint, in addition to a custom domain name on top of that. So you may ask, okay, why do I care about a custom domain name on top of it? So it's just a vanity URL, but it helps from a deployment standpoint. So what could potentially happen is if you're doing things like, I need to actually take down this API and maybe redeploy it as a new resource. Again, you may have some production issue or something event happens. If you have applications that are pointing to that API with the AWS vended endpoint, so it'll be something like API ID.region.Amazon AWS, or it'll have execute API.AmazonAWS.com, and then / your stage / whatever the resource might be. And if you're injecting those, maybe you're using secrets manager things or parameter store, it's just another configuration that may need to change in the future when you're integrating your applications. Now that tends to be why customers want to be able to do things like custom domain names. And so this is a solution that was put together. Actually, George, again, wrote a blog about this on his personal blog, actually, and wrote about it like 2 years ago. This is like a workaround solution for the time being, while the API Gateway team is working on this feature capability. So this is an architecture solution. Again, I won't go into the the weeds on this one, but the basic idea is you can apply a certificate on top of a load balancer, and then that load balancer will essentially talk to your private link interface endpoints, and then that can then talk internally to the API gateway service and essentially route that traffic to the API gateway in the back end. There is a link there at the bottom. If you're interested in more details, it's a link to a code repository where we actually implement this full solution. And it also has a link to George's original blog that actually talks about this solution. Now, I've also had customers that have said, that's great, and this helps me secure my APIs privately. It gives me that vanity URL in front of my endpoint to make sure that I have kind of resilient integration for my APIs. But I also have things like multi-region requirements as well. So you could imagine if you're a regulated industry and you now have requirements that you need to have a secondary location X number of miles or kilometers away, you may have a multi-region requirement there. And so the basic idea here is, again, there is another repository that is actually linked off of the original one. It essentially extends that solution. It adds a transit gateway solution in there where it can actually connect the VPCs and have that type of communication. You can then use a Route 53 alias on top of that to be able to do that communication. So this is just, again, one of those resiliency patterns. At AWS, we're trying to make this easier. Again, our API Gateway team is working through solutions and thinking through making this experience for you as a customer better. It is a work in progress. Now, part of the reason why we want to talk about multi-region is because, again, Capital One does have this requirement, and George can talk about your architecture.
Yeah, so this architecture represents what we call platinum resiliency, and the idea is to be able to drive our entire business workload 100% in one region or in another, right? So like Werner always says, everything fails all the time, right? And so you have to design, even in AWS, you have to design your architecture so that you expect failure. So at a very high level, the bullets on the right are the things that we're trying to achieve, right? So dual region resiliency is super important for us. And the way we do it is we actually deploy the same API stack in 2 regions. And we can either operate 50-50 or we can operate 100-0. And we flip that across all the time, right? We flip it even when there's no reason to, right? Even when AWS is not down. We perform exercises so that we ensure that our teams are able and ready to do this. And the way we make it work is we have a high-level Route 53 hosted zone. And it's got 2 entries, right? So it points to one in one region, one in another, and then the 2 regions have the exact same tech stack, right? So for our serverless offerings, we have ALB that fronts Lambda, and then that ALB invokes Lambda functions using the same traffic shifting that we just talked about in the couple past slides. So we have that live traffic standard. Like every developer understands how this architecture works. They can switch teams really easily. We use CodeDeploy to make that happen behind the scenes, and then Route 53 CNAMEs. Like those are the primary technologies in place here, and they really help us make sure our business runs 24/7, so we don't have any kind of outages. Yeah. Cool. So we're going to jump into some interesting errors that we have encountered. And hopefully, if you see these errors, you'll be able to get through these quickly. So for those who have used provision concurrency, you know that it will allocate your Lambda functions. It'll run the initialization phase as soon as you turn it on. Like as soon as you say, I need X number of PC on your function. If there's any kind of error in your initialization, your allocation will be entirely blocked, right? There's no way to recover from that, at least no way that we've found. Maybe Higgy can help me next week when I go back to the office. But in this code example, line 2, it's just a very simple example. I hard-coded an error, so it just says throw an error. This is an initialization error. The only place you'll be able to see that there was a problem during initialization, that's in the Lambda console, right? It just says, status failed function error init failure something 0 out of 1, right? So this will block your entire rollout, and this will cause confusion, and developers won't understand like where this is coming from. So just make sure you're very careful about your initialization block, and you understand if there's any errors in there. You can perform logging in there, and you should, right? So make sure you watch out for that if you're using PC, and Hig is going to keep us going on initialization.
Yeah, so another thing to think about, this may be kind of a well-known, perhaps hidden secret. So one of the things that you may be aware of is with your on-demand Lambda functions, there's certain CPU behaviors for that initialization period. So kind of the best, the most well-known, not so secret about CPU burst is you actually get free CPU burst in your on-demand attempt. So kind of one of the best practices that we often recommend to customers is in your on-demand initialization phase, put as much compute as possible in that phase, because what we essentially will do is we'll give you a full vCPU allocated to you, and we'll essentially give you 10 seconds to do as much computation in that phase. And so George is actually going to momentarily walk through some testing that they've done to kind of observe some of these behaviors. But what happens is if, for example, you are doing a large amount of initialization or a large amount of compute during that first 10 seconds, and perhaps you time out, what will happen is that first initialization attempt will actually fail, and then you'll go into a second attempt. And that second attempt will then operate perhaps what you might normally expect, which is you will use the vCPU that is proportional to the memory that you've allocated to that function. And the timeout will no longer be 10 seconds on the second attempt, but it will be whatever you've configured for your function. So for example, if you've configured 60 seconds as the timeout for your function, your initialization will be subject to that 60-second timeout period. Now, the experience of that on-demand second attempt is actually what happens for PC. So when you're initializing your provision concurrency, you don't get that CPU burst that you might have expected. You actually get the proportional CPU, and again, you'll be constrained to whatever the timeout might have been for your actual function configuration. So George is actually going to share some cool, you want to go through that?
So visually, this is just a representation of the life cycle of a Lambda function, right? On the left is the initialization section. It runs everything during what you would call a cold start. And then during a warm start, you just invoke, 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 and those are really fast. So in general, memory is directly proportional to CPU power. So if you double your memory, you double your CPU power. You have your memory, you cut your CPU power in half. So the side effect that Higgy was talking about is not in the documentation. So getting full burst CPU during the init is something that you kind of just have to know. It's kind of a secret. So we do a lot of heavy lifting in there. So we do encryption, decryption, a lot of CPU-intensive stuff, and it runs a lot faster, right? And it's basically free, as long as you stay under 10 seconds. So I'll show you how this works. This is just a piece of really simple code. It's not production grade. It's just meant to simulate a very compute-intensive application. And all it's doing, it's calculating SHA-512 hashes, right? So, and it's putting it in a 10,000 iteration loop. So I don't think anybody would write code like this in production, right? But the purpose is to calculate how long it takes to run this, and then run it against different memory allocations so we can see how this impacts Lambda performance. So our first test, I ran this test at, we run this code both in the initialization phase and in the invoke phase of your Lambda function to compare the results. So in the first red box there, this code takes 0.9 seconds, so just under a second to run in the initialization block. And the bottom red block is during the warm invoke block. And you will notice it runs 3.12 seconds. So it takes a lot longer, right? Now, let's double the memory. Let's go to a gig, 1024. And remember, doubling memory doubles CPU performance in general, right? So we notice that the initialization hasn't really changed that much. It's still 0.88, right? Because you're getting that full CPU burst, and it's not changing with your memory change. Now the difference at the bottom there, we run during the warm start, during the invoke, is 1.5 seconds. So that's basically half of what the 512 meg was running, right? So what do we think the next step is? Our third test is we're going to double memory again to 2 gigs. And the the performance we're after is another 100% increase. So we go 2 gigs here. We're at 2048 for our third test. And again, our initialization phase doesn't really change, like 0.88. And then we finally have a equivalent invocation timing during the warm start, 0.88. So every application has a break-even point. You're going to find at some point that your code cannot run any faster on the hardware that AWS gives us. Right? So this is it. We've found exactly where your memory should be for this application. Right? So every Lambda engineer should go through this process. Right? You should be tuning your memory to understand where that break-even point is for your function. Because if you aren't, you're either performing too slow or you're just provisioned too high and wasting memory, right? So AWS prices your Lambda function on the memory configured and not on the memory used. So that is why we want to go through this process, right? So just to prove this out, we go up another gig to 3 gigs of memory, and we see that the performance on the bottom doesn't really change anymore. So if I were to be running in production and I ran at 3 gigs instead of 2 gigs, I'm 30% over-provisioned and paying Higgy 30% more, right? So it's a really fun process. There's a little bit of art. Every piece of code is different. Every library you use is a little bit different. So you just have to play with this, right? So this is just a quick summary. The init phase is full unthrottled CPU. Doesn't even charge you money. Do your heavy lifting there if you can. Make sure you don't exceed 10 seconds, because AWS will kill the init, restart it, and bill you for it. So provision concurrency does not have this feature, right? But it doesn't really matter, because you would provision concurrency up ahead of time and use that allocation when it's ready to serve traffic. So
yeah, I'll take this one. So you might have said, hey, that's great what you did. That sounds pretty labor intensive to have to go through all of that testing. So an AWS solutions architect said, yeah, a lot of our customers are going to want to do this. So you may be familiar, or if you haven't, there's an open source tool called Lambda Power Tuning that's available. So there's a link there at the bottom, which essentially will do the same process that Georgia just described. It essentially uses an AWS step function, which is essentially a state machine that will kind of go through a number of different configurations. In this tool, you can provide and say, I want to optimize for performance, or maybe I want to optimize for cost. And you can actually specify as an input parameter different memory configurations. So you could, again, specify 128, 512, 1 gig, and then whatever other increments you may want to. And using that step function, what it will do is it'll automatically load test, essentially, or execute your function against those different memory configurations. It'll collect all of the data, and you'll see this graph here it actually produces you a nice output. So it'll actually say, here's the performance in terms of duration against your memory configuration, and then it helps you to visually see where is that sweet spot. So the work that George just did, had we just done a power tuning step function, you would have actually seen that that 2 gig mark was kind of that sweet spot. So again, this is kind of one of those ways. The other interesting thing is when we announced ARM support for Lambda, I think about a year ago, this power tuning was actually updated to enhance so that you can actually run multiple architectures, so that if your code is compatible both for x86 and for ARM64, you can actually produce a graph like this and overlay both x86 and ARM64 on the same graph. So you as an organization can say, hey, is ARM64 actually an architecture that we want to investigate to potentially give us better price performance? So this power tuning tool is, again, open source and available for you as a customer to try out. All right, next one, the one that I'm very excited about. If you were listening to Peter DeSantis' keynote last night, you may have heard about this new capability called SnapStart. So how many folks in here for your Lambda functions, how many of you are writing your code in Java? OK, actually not that many. Interesting. So maybe not as exciting for you. But for many of our customers, so I work with a lot of enterprise customers. A lot of them have lots of Java code within their organizations. And as we think about it, if you're building like a net new use case, maybe you're going to write it in JavaScript. Maybe you'll write it in Python. Maybe you'll write it in an interpreted language. But for organizations, as you start to think about modernizing existing applications, you have large code bases, and you want to maybe think about moving them into Lambda. Maybe you have lots of dependencies that you've built all of your business logic into, and you want to bring that into your Lambda function. So one thing that we've seen some of our customers talk about is, in general, when you're kind of initializing your Java-based Lambda functions, they tend to be a little bit slower than the interpreted languages. And this is primarily because you have that JVM. And so we can kind of talk about it here. This is essentially what happens when you're essentially invoking your Lambda function. Really on the back end, that cold start that George was talking about before is going through these 3 basic steps. Essentially, we're going to download your code. So you've created, let's say, a jar artifact or maybe a Python zip file, something to that extent. We're going to download that and cache it locally within the Lambda environment. We then start what we call the runtime environment. So again, if this is a Java-based application, we're going to start up that JVM. And then we'll do the initialization. So the initialization would be things like, I'm going to do some static code initialization, anything outside of that handler block. So before, George had that, the SHA-256 code that was running outside of the handler, but then he also wrote it inside of the handler. And then, of course, there's the invoke handler, which would be your warm start. So things like, actually, we'll talk about it momentarily. So the question is then why? What does this get me? So the interesting thing is we did a bunch of performance analysis, and we started collecting data. And the interesting thing is that the typical overhead of downloading the code and starting the runtime environment, again, give or take a few 100 milliseconds, is roughly 1 second. That's the overhead of your Java-based runtime execution environment within your Lambda world. Now, for you as a customer then, suppose I want to do a Spring Boot application in a Lambda function. For anyone who's done Spring, you'll know that the startup of that Spring environment or that Spring framework can be something in the order of 6, 8, 10, maybe even 12 seconds if you have not that many dependencies for that framework. And so you can imagine that could be very painful, especially if you have an API and you have a synchronous workload, and you have an end user on a mobile device or on a web application expecting a synchronous response back. You have a cold start that's 12 seconds. As you can imagine, that's a terrible customer experience. Now, with SnapStart, sorry, didn't mean to go. So what we do with SnapStart is that we will do all of that initialization ahead on your behalf. Sorry, actually, I skipped ahead. So some things that we see our customers doing to avoid that ahead of SnapStart is things that George has talked about. So they've done things like provision concurrency. You may have heard of things like GraalVM. So you could do ahead-of-time compilation, compile it down to a binary, and then run that in a custom runtime for your Lambda environment. Now, what SnapStart is going to do here is all of that initialization, so the downloading the code, starting the runtime environment, initializing the code. So again, if you had that Spring framework, it was taking 10 seconds. That all happens ahead of time. Then what happens is we will then take a snapshot. So we're using the Firecracker micro VM underneath and using that technology to then create a snapshot of that memory space. What we then do is when you, as a customer, do an invoke of your function, and it is a cold start, instead of doing all of that initialization, we're just going to resume that memory state, that snapshot that we had just created, and we'll resume that. And so we've seen some really good performance results that George will go through momentarily, and then you go ahead and do your warm invoke.
Cool. So we had the opportunity to test SnapStart for a little period of time during the beta, and these are the highlights that we found. So for us, many of our Java-based apps, I'd say more than 50% of them have Spring and Spring Boot in them. So they were seeing 15-second cold starts, right? So that's not a good customer experience, and it generally will not meet any API SLA that serves production traffic. You do have to use Amazon Credential 11 as your runtime. So you will have to upgrade your Java runtimes to 11. In general, that's a pretty light process to bump your Java runtime. There's very little code changes that are needed, if any at all. It's generally all done by Amazon. You do have to provision a new version of your function, but that's not a code change, really. All up, every test that we have combined together, we saw roughly 88% cold start reduction. So something taking 15 seconds was down to like 1 second. And this allows us to move a lot of those legacy Java apps into Lambda and get all the advantages of Lambda and move into a serverless world. So there's a lot of apps sitting on EC2 that can benefit from this kind of stuff. All right, so this is the next slide is basically a sample of some performance improvements and different use cases that we've seen. On the right is basically the percentage improvement that we're seeing. If we look through the different types of applications, almost all of them have Spring and Spring Boot in them. If you see anything that has like 74%, 94%, 91% improvements, those are all Spring-based applications running with Java. The one I want you to look at is the one in the middle, Java API application with Netty and Dagger. This one actually doesn't use any Spring. So we saw 15% improvement in this case. So what that means is like even your Java apps that don't have heavy Spring, Spring Boot, all of those injection reflection libraries in there, you will still benefit from this. So at Capital One, we haven't made a final decision, but we believe that SnapStart is potentially should be the default strategy for anyone doing Java-based Lambda functions. So highly encourage you to test it out. We've seen really great results. It was launched yesterday at the Peter DeSantis keynote last night. So there's a couple caveats that Hickey will walk you through. So just pay attention to some of these as your developers work through them.
Yeah, so we'll just do a couple quick FAQs. So these are things, and I'm sure that this list will continue to grow as we kind of observe some maybe some pain points or unexpected kind of experiences. So the first one is as you're writing your Lambda functions, of course, maybe you're making SDK calls to other AWS services. Of course, you'll need to have credentials to be able to make those calls. You're going to want to get access to those credentials. So normally what you might have done was maybe you're using the default provider, or maybe you're using the environment variable provider, right? So within the Lambda execution environment, you actually have access to your access key and your secret key, and you can actually make use of that through that provider chain. Now, one thing that's interesting is that the environment variable credential provider does not work with SnapStart. And you may ask, OK, why did you just kind of break some of the SDK experience? Part of this is because of, if you remember that slide, when we're taking that snapshot, we're going to store that snapshot for some period of time for you as a customer, and we'll have that locally cached. Now, what you want to be careful of is, if you remember, your IAM credentials are essentially short-lived credentials. And what you don't want to have is those short-lived credentials to exist within that snapshot. Then when you do a restore, your execution environment will then rely on credentials which are essentially expired. And then you'll have that error that you'll have to make sure you catch within your function and then essentially get a new set of credentials. So what we've done is to prevent you from having that experience. We've essentially taken that out of the provider chain. And the bottom two are essentially the two that you're going to want to use. So again, just beware if you're looking at testing SnapStart and you're using the environment variable credential provider, you will want to make that update. Things that other customers are thinking about is, how do I know if I'm kind of in a resumed snapshot? So this is, again, another environment variable that will give you awareness. So some customers may want to know, is this, sometimes they'll want to know, am I in the initialization phase, or am I a warm invoke? And in this case, you can actually see this was actually a SnapStart invoke. Another one here is some customers may say, hey, I enabled SnapStart, doesn't seem to be working. Why am I not seeing the benefits that George just talked to me about? Maybe you guys are lying to me or something. Right? And so the thing to be aware of is that SnapStart is enabled on versioned Lambda functions. So if you're Capital One and you have the live traffic alias and everything is automatically versioned, they probably didn't even notice the fact that it was on that. But maybe if you're actually using latest, $latest on your Lambda functions, you may not see, you will not see the SnapStart improvements. Again, if you're also using versions but not aliases, and again, you're invoking based on the direct versions, but that version didn't actually have SnapStart enabled yet, again, that may be another reason. So just be aware. The same concepts, if you're used to using provision concurrency, the same concepts apply. You want to make sure that that version that you're applying has, either, in this case, the SnapStart enabled. Likewise, on database connections. So again, George made allusion to this before around scaling, maybe using things like RDS proxy. Again, I know at Capital One they don't use that. But likewise, you can imagine when you're initializing your functions, you may want to create that database connection, again, outside of the handler. You wouldn't want to be doing that inside of the handler. So on initialization, you're creating a database connection. But again, you remember that we're taking a snapshot, and that could be perhaps a day later where that warm invoke or that resume snapshot comes in, and that database connection would have been severed or terminated by the database server itself. So what you want to be aware in this case is during your warm invoke, you just want to test the existence or valid, that the connection is still valid. And if not, in the invoke handler, you will want to then reinitialize that connection. And then, oops. The other key one that we want to be very careful about is around random number generation. George alluded to this a little bit in one of his slides, is that if you are dependent on random number generation, and you may be because cryptography, as an example, so cryptography and thus SSL, so any type of secure communications that you're reliant upon within your Lambda function will have this impact. So there are a number of libraries out there that are essentially what will be good within the snapshot environment, or you could even use, for example, I think there's the dev urandom, which are good for you to be able to use. All right. So George is going to kind of walk through some kind of best practices that they've experienced.
Yeah, so we have, I'd say thousands of Lambda functions deployed and running at any given time across our entire serverless fleet. And these are like the things that I've discovered that you really shouldn't be doing. And if you're doing them, you should probably have like a peer review and understand why you're doing them. So every time I see one of these happening in our engineering environments, these are kind of like red flags. So take these back with you, put them in your standard code review process or your design processes, and make sure you're doing these with good reason, right? So the first one is important. If you're setting maxed out memory every configuration for your Lambda functions, you probably haven't done your job in optimizing that function. You're just setting the max peak. And the risk here is that if your functions run to the 15-minute max and use 10 gigs of memory, it's going to cost a lot of money, right? You're going to be sending Higgy a lot of money. So we don't want to do that. Second is, who's used reserved concurrency before, what we call RC? OK, about a third of us. Now, reserved concurrency is actually different from provisioned concurrency, right? So reserved is just an artificial configuration cap. It says my function cannot run higher than the number I set. It doesn't actually do anything for you. It doesn't warm it up. Provisioned concurrency warms it up. Now, if you're setting these two values equal to each other, what that means is your provisioned concurrency will take all of the allocation that you set RC on, and you'll never be able to run on demand. Like, you'll never be able to spill over. If you have additional traffic, it will just throttle, right? So this is something you definitely want to avoid. Related to that is you don't want to really over-provision concurrency at peak traffic, right? Because that means you're going to be wasting compute power all of the times. I'm not going to go through every single one of these, but number 6 there is important. If you're using any one of the event sources that are like batch-based or polling-based, so SQS, Kinesis, MWAA, any of the ones that AWS polls on our behalf, you generally don't want to set the batch size equal to 1. Because what that's going to do is it'll tell the Lambda poller to grab one message or record out of that resource and deliver one invoke to your Lambda functions. And that's incredibly inefficient, right? So you want to set that batch size bigger than 1 and handle the batch in your code, right? Handle that looping in your code. And then number 7, I had it up here, but I crossed it out because SnapStart launched yesterday. So we didn't like Java and Lambda and Spring together, but with SnapStart now, it's feasible, right? You should start investigating Java-based functions now. OK, so next slide is some best practices that we've found that are really helpful, both for security and for performance. Number 1 there, who has set a CloudWatch log retention policy for your Lambda functions? OK, so about half of us. The reason you want to do this is because CloudWatch logs are incredibly expensive. And in some cases, it may cost you more for logs than your Lambda compute. And that is never something that we want to see as customers, right? So in general, I think it's something like 53 cents per gigabyte stored in CloudWatch log. And if you never expire them, they just pile up and get bigger and bigger and bigger. If you do a load test on your Lambda functions, like I don't know how many gigs of logs you're going to generate. Right? So especially in your lower level environments, expire those logs 3 days, 7 days, just get them out of AWS. In the upper level environments, obviously match your expiration policy with your data retention policy. Next two and three, just optimization is always key, right? Optimize for architecture, optimize for memory. Don't give AWS like that extra overhead cost, right? Last thing here is when I work with our engineering teams, the number one thing that I say is make sure you estimate your serverless costs, right? Have your teams understand like what that new application will cost. In general, it'll be much less, but the big thing is just hop onto the AWS pricing calculator. It's like aws.calc, right? And it just put in the Lambda functions, put in the settings you think you want it to be, and then change them around and play with them and see how those settings impact your environment. Number 7, so Lambda has a 50 meg deployment size limit if you're using zip files. Right? You cannot go bigger. This is a hard limit. That doesn't really mean you should deploy 50 meg zips, because Higgy talked earlier, that first process that happens in initialization is AWS goes to S3 and it downloads that zip. Right? It happens really fast. But if you're deploying a 1 meg zip, that happens a lot faster. And unzipping it is also much faster. So take out source code from your zip files. Take out anything that's not part of what you actually need to run. Minify your code. Remove unnecessary dependencies. Get rid of dev libraries. And really compact your Lambda functions. And you'll find that you can cold start in single-digit milliseconds. It's really fast, right? And then last thing is, this gets overlooked a lot. Always look at your metrics. AWS gives us everything we need to look at how your functions are performing. Everything from duration to throttles to memory performance, like everything is there in CloudWatch. You just need to go build a dashboard and look at it. So that's basically it. I think that these are the top things everybody should be doing. And I like to leave everybody with this quote. Has anybody seen Spider-Man? Everybody, right? So Lambda gives developers the power to do everything. So you have to be really careful with what you're doing. And just watch everything from the past 2 slides, right? Things to do and things not to do. And I think you'll have a good experience with serverless.
Yeah, and so if you want to kind of continue that journey, so we are actually announcing kind of this new serverless learning path. So there's this kind of opportunity. It's not quite a certification, but it allows you to essentially earn a badge. So you can start to earn badges against certain specialties within the AWS environment. And here's the one that you can do actually specific to serverless learning. And in light of continuing that serverless learning, there are a number of sessions. Again, I didn't track the timing of all of these, but these might be other sessions that you may be interested in that may be relevant for continuing your journey. So we want to say thank you to everyone for coming, and hopefully you were able to learn a lot from this session. So thank you very much.
Yeah, thank you.